Hi, you guys. You're making a better video for our sections 2 and 3 out of chapter 18. Still on electrochemistry, still talking about corrosion. This is rust. We're not going to get there yet in this video, but I just like to draw rust. What we are going to get to is determining this voltage idea. What is voltage? How is voltage created between two separated, what's called half cells? This half cell here has a zinc and zinc nitrate in it. This is copper and copper nitrate, hence the blue color. This is a very common cell called the Daniell cell. The Daniell cell was one of the very first really studied cells. Don't know why, but it was. The Daniell cell was this copper zinc cell. But either way, when you set up a Daniell cell such as this and you plug it into a voltmeter, you get a voltage, and that voltage is 1.10 volts. Now the question is, where does that voltage come from? And how can we track it? And then how can we assign a voltage to the zinc and then assign a voltage to the copper? That's what we're going to get to in this video. So first, let's look at galvanic cells. A galvanic cell is what you just saw in that previous cell slide, which showed the zinc copper cell, the Daniell cell. It is a way to harness electron movement and through a device. This is done by separating these half cells. If you took a chunk of zinc and you stuck it down in this solution right here, you would see copper metal grow right on the surface of the zinc. Now, why does that occur? It occurs because zinc is more active than copper. Remember from your activity series from chapter 4 in Chang chemistry, we saw that copper is less active. So copper would rather be copper metal when compared to zinc. So sure enough, you can still get this to occur, but it occurs through electron transfer through a wire, and then you can tell that electron transfer is occurring or something's happening. You can do work with that electron current through a device such as a light bulb or some little device, little motor, or however you want to use it. Either way, a galvanic cell, also called a voltaic cell, after volta, is a cell where you have two half cells. This is the zinc half cell where oxidation is occurring. The copper half cell is where reduction is occurring. Anode is where always is by definition where the oxidation occurs. You can see an oxidation reaction right underneath here showing the oxidation half reaction. The cathode is where reduction occurs, and you can see the reduction half reaction. So of course, if you add these two reactions, your electrons are going to cancel, and your overall reaction is going to look like this. So this is the spontaneous reaction that occurs between copper and zinc. It will always occur spontaneously. This is the downhill thermodynamically reaction that would occur between copper and zinc. So let's keep going here on our understanding of a voltaic and galvanic cells. This is a drawing that you would do for fun sheet question number 3, except I gave you different half cells to use. So let's go to the next slide, which is going to continue our discussion of voltaic cells. This is the same picture you saw in the very beginning. There's that copper and zinc, and there's this 1.1 volts is what we're going to talk about here. These half cells have a difference between them, and that difference is called the cell voltage. This one happens to be 1.1 volts. You can see it registered over there between this copper zinc cell. It can be called electromotive force or cell potential. Now, this cell potential is different for every combination of half cells. It can be the same number for a different combination, true enough. This reaction that you're seeing happening above here is that zinc and copper, that Daniell cell. By definition, so we can standardize some things, we are going to make the 1 molar concentration for both of these. Check it out. Those are both 1 molar. What we're going to learn about now is called a cell diagram. A cell diagram is a shorthand method for writing the process that occurs within a cell reaction or an electrochemical reaction. By definition, the anode is always written first. Zinc is being oxidized to zinc 2+. Copper is being reduced to copper metal. These lines here are phase boundary. The phase boundary is between the solid metal and the aqueous cation solution. And then our salt bridge has to be in place, and you can see it up here. It looks like a little U-tube, and this U-tube has a salt solution in it somehow to be able to transfer charge between the two half cells. If you did not have the salt bridge, you would quickly build up charge in either one of these containers. Since oxidation is occurring on the zinc side, you would build up a positive charge if you did not have that salt bridge. If on the other side, you would build up negative charge since positives are disappearing. I encourage you to go watch that video that I posted in the discussion board, and that will help you understand how these voltaic cells work and help you draw your picture for your fun sheet. You might want to go do fun sheet question 4 right now. That is for drawing a cell diagram for a certain cell or drawing a chemical reaction from a cell diagram. So, assuming you've done those fun sheet questions, let's go on to understanding that 1.10 volts. What is that? That 1.10 volts. Where does it come from? How is it measured? What is a standard? So we're going to standardize some things here. Standard reduction potential. It's the voltage associated with a reduction reaction. Reduction reaction. At an electrode, when all solutes are 1 molar and all gases are at 1 atmosphere. Now, this is a standardization that has been standardized to what's called the standard hydrogen electrode, or the sheet. That means every element or other half cell reaction has been coupled to the sheet, the voltage measured, and tabulated. So this has been defined as a 0 volts. It's been defined as a 0 volts so we can understand the other half cell reactions with respect to it. So let's get going here. In this example, zinc, that zinc half cell, like you saw in the previous Daniel cell, has been coupled to the sheet. When that happens, you get a voltage of positive 0.76 volts. When something is spontaneous, it will always be positive. And that positive just means it's spontaneous, that's all. So when this is set up and the voltmeter registers positive 0.76 volts, that means that it is spontaneous. Now the question is, who's being oxidized and who is being reduced? That's a good question. Through experiment, it was found that zinc is being oxidized with respect to the sheet. Check out this little cell diagram. Zinc is oxidized to zinc 2+. Hydrogen ions are reduced to hydrogen gas. That is the spontaneous reaction for this pair. So looking at your half reactions, you will see that zinc is oxidized, hydrogen is reduced, and there's your overall reaction when you couple the zinc with the sheet. What about the number? Now the number that goes with this is positive 0.76. However, by definition, the electromotive force of the cell, which consists of these two half cells, this is a half cell and then this is a half cell, by definition is the cathode half cell EMF minus the anode. Now the question is, who's the cathode and who's the anode? By definition, it was found that zinc was undergoing oxidation. That means it must be the anode. We have already defined this guy to be 0, so check it out. Here's our cell diagram. Recall, this guy is equal to 0. And since it's equal to 0, and this is equal to positive point, this is the one that's unknown, but we know the whole thing is equal to positive 0.76, we can solve for that half cell. Turns out to be negative 0.76. So this negative right here means that when coupled with the sheet, it was oxidized. And there you have it. And this is the number that you would see in our table 18.1. So you might want to make a copy of table 18.1, have it next to you at all times, because it's a reference source that helps you understand what's going on. So that was for the zinc. Check out the copper. When we put the copper together with the sheet, we find that copper is reduced when compared to the sheet. So here is our cell diagram and our half cell reactions. When this is set up experimentally, it's determined that copper is reduced and hydrogen is oxidized. That's why now this is on this side of our cell diagram, and the copper is now occupying the reduction side. Add them up, you get the overall cell reaction. Spontaneous cell reaction, where hydrogen is oxidized and copper metal is reduced. So what does that mean for your half cell EMF for the copper? Well, from experiment, we see that this 0.34 was what we measured for the overall cell, still assigning this guy to be 0. This now must be positive 0.34. Since it is positive with respect to the She, that means it is preferentially reduced compared to the standard hydrogen electrode. So let's keep going. I created this slide because it's interesting to see that when we coupled with zinc with the She, we got an oxidation. When we coupled the copper with the She, we got a reduction. Now, what would happen if you couple the copper with the zinc? Because now we're trying to explain where, if you recall, that 1.10 volts comes from when you couple zinc with copper. So again, cathode, anode, but now, I'm sorry, that kind of zipped in there. Now the E of cell, remember, is cathode minus anode. The anode is 0.76, but is it 0.76 or is it negative 0.76? That's a good question. Let's look at that in a moment. Here you have E of cell, cathode, anode. Let's put them together. Notice this was negative 0.76. That is the anode with respect to the She. Even though it's positive over here, it became negative once we solved for it. And then this guy's positive minus a negative gives us a positive, and there's that magical 1.10 volts that shows up on the multimeter. You will be doing a virtual experiment where you can set up all different half cells and see the results of the voltages. So now let's look at the tabulation, table 18.1 that I mentioned earlier. What does this table mean? This table is tabulated as reduction reactions as written from left to right. You see that? They're all reductions, meaning the electrons are written on the left as a reactant. What does this mean as far as it's kind of like an activity series? The more positive the E, the greater the tendency for the substance to be reduced. And when we say substance, we mean the substance on the reactant side. So if you look over there, F2 really wants to be reduced, which we know to be true of fluorine. If you look at the bottom of the table down here, you can see that lithium ion does not want to be reduced. So that's why it has an extremely negative E of cell, E of your half cell. And they're all reversible. And if you do reverse them, of course, your EMF reverses its sign. But I caution you against doing that because when we do our half cell reactions and our cell reactions, when we're going to calculate E of cell, keep them the same. If you want to flip them so you can add up the chemical reactions, that's fine, but keep the E of cell sign as it is on the table. If you change the stoichiometric coefficient of the half cell, the reaction does not change. It does not change its value of E. And the reason is because this is a potential difference between half cells. It is not like how far is it running downhill. That's what this is really showing you. It is not showing you the number of electrons that run. If I multiply any of these guys by a factor like 2 or whatever, it does not change the voltage over here because that would change its location in the table. Its location in the table remains the same. Let's keep on looking at this table. This table, well, let's read this first to see what we can figure out what it's asking. The more negative or positive the E in this half cell, the greater the tendency of the substance to be reduced. So the reduced was at the top. So the more positive the E, the greater the substance is to be reduced. And when you said substance, that meant the reactant over here. So at the very top left, like fluorine really wants to be reduced. So it is a very strong oxidizing reagent, means it'll steal electrons from somebody else. The bottom left, on the other hand, is the weakest, just like lithium on the previous slide I was talking about. So the top right would be something like fluoride. Is fluoride weak or strong reducing agent? Well, remember, a reducing agent gives electrons. Does fluoride want to give electrons? No, it wants to keep. So it's going to be the weakest. The bottom right is going to be the flip side of that. The bottom right would be something like lithium solid. And remember, lithium solid very much wants to go to lithium positive. So since it wants to go to lithium positive, that means it's a very strong reducing agent. Okay. Now I have to do fun sheets 6 and 7 here, because on the fun sheets 6 and 7, it's asking you who will reduce who and vice versa. And that's all dependent upon its location in this table. So see if you can do that. Post a question to the discussion board. Our next slide is discussing substances that we can try to figure out from our table here if what's going to happen spontaneously. And I call this the magic X. You can see a magic X right here. It's an X. I don't know if it's magic, but I call it a magic X, which is going to indicate the spontaneous chemical reaction between two substances given their location in table 18.1. So if we have two, we just picked two half reactions in here. The reactants are going to start with number 1. This is the reactant, and then the other reactant is going to be number 2. So this would be the other reactant in the spontaneous chemical reaction between hydrogen and zinc. The products are going to be 3 and 4. So here are the products, 3 and 4. I just chose 2 half reactions from table 18.1. And you see what I did here is I cut this table in half. I cut everything below the sheet. Everything below the sheet is going to reduce hydrogen ions to hydrogen gas. And then hydrogen ions will oxidize everything below it to the respective ions. So check out the reaction that then occurs. This is the spontaneous chemical reaction between hydrogen ions and zinc. Now if we check out the EMF, check it out, you run across here and you see that negative 0.76, and that negative 0.76 is what was determined by coupling it with the She, hooking it to a multimeter. And we got positive 0.76, but we had to flip it because it was being oxidized. What about for a reduction? I've done the same thing for this table. I copied the top half of the table, and this top half is a stronger reducing situation when compared to the She. So I chose 2 half reactions, the MnO2 reaction going to Mn2 plus and water in an acidic solution, notice, and then compared it to the She. So if I combined manganese 4 oxide, you would see manganese 4 being, remember this is this is plus 4 here. We're seeing a reduction occurring for manganese, and we're seeing an oxidation occurring for hydrogen. And that's because everything above the She in this part of the table would rather be reduced. This guy's plus 2, that's a reduction. So notice the numbers. These numbers have been determined by coupling them with the She. So this is a reduction reaction that's occurring here compared to the She. So let's ask a question here. Using that table, can tin metal, this is a metallic substance, can it reduce zinc 2 plus under standard state conditions? Well, from table 18.1, I've written them such as 18.1 as where they would be. You see the positive one, this guy is more positive than this one, than this guy is. So this one would act as the cathode. This one would act as the anode. But that's not what's being asked. What's being asked is, can tin metal reduce zinc 2 plus? Now remembering your magic X starts with a 1, goes to 2, goes to 3, and goes to 4. 1 and 2 are the reactants, 3 and 4 are the products. What would spontaneously occur? Tin 2+ would react with zinc solid to make zinc 2+ and tin solid. That's spontaneous. They're asking you, can tin metal reduce to do that? And the answer is no. It does not spontaneously. We can cause it to happen by hooking it up to an electricity source, but currently it would run downhill the other way. So as far as doing a little bit of practice with this, now let's look at some numbers. They're asking, what is the standard EMF? We need the numbers from that table. So let's do an example of cadmium and chromium. From the table, the more positive one is written first of the 2 half cells. That means this guy is going to be cathode. Cathode is more positive. That's how I remember it. There's that positive right there. The cathode is going to be the more positive of the 2 and will undergo reduction. The negative will be the anode. The question here is, what is the standard EMF? The anode will be the chromium. I just showed you that up here in green. The cadmium will be the reduction. Now notice what happened here. This one has been flipped. That's fine. You can flip it. And if you flip it, when you add it up, your electrons cancel, which is what's important. Do not flip the number when you do actually do the determination of the E of cell. Here's your overall reaction then. Chromium solid reduces cadmium metal to make cadmium metal and chromium 3+ in solution. How do we do our E of cell? We go get the numbers, but notice we don't change the signs. This sign was and your overall E of cell is a positive 0.34, which means spontaneous. When you do something from the table like this, it should always be spontaneous, and you should always have a positive E of cell. Now go try funky question 5 and 8. That will help. This example will help you with that.